Welcome to the office. In this video we're going to talk about Chapter 2, Section 3, which is about calculating limits using the limit laws. I'm going to go through some slides that follow along with and sample from Stewart's 8th edition calculus book. And then we'll toggle over and look at some homework problems in WebAssign. And this section shouldn't be too taxing for us. I think you're going to find that the limit laws are quite intuitive, and I'm going to try to keep the volume levels up. I've heard some of you say that the volume's a little bit low, so I'm going to push it into the red a little bit, and feel free to give me some feedback. Let me know if everything's coming through okay on your end. And without further ado, the limit laws. Let's go and see if we can find them. Here we go. So these limit laws are telling us, and I keep drawing with my finger. I don't know why that happens. There we go. First of all, we're being told that the limit as x approaches a for f of x, and we're going to be looking at the limit of g of x as x approaches a. So these are a couple of expressions that we're being told that we're going to look at. C is a constant, and in number 1, this almost looks like the distributive property of taking a limit over addition. And it pretty much functions that way. The limit of the sum is equal to the sum of the limits. And in number 2, it applies the exact same way to subtraction, because addition and subtraction are essentially the same function. In number 3, we see this c value inside of our limit multiplying the entirety of the function, and number 3 tells us that we can factor that c value out of the limit process. We could then evaluate this limit and then multiply whatever result we get by c. In number 4, it looks like we can distribute the limit across a product. So the limit of a product is equal to the product of the limits. And in number 5, it almost perfectly applies to a quotient also, except we have to make sure that the limit of the denominator does not end up going to 0. And we'll see a problem as we go along where that is the case, and sometimes we'll be able to do something about it and sometimes we won't. But it is definitely something to watch out for. These are verbal explanations of those same laws that we were just looking at. You're welcome to check those out. And then we'll start talking about some examples. So we can use our limit laws to answer the following questions, and I like the way that these questions are formatted. At least it brings in a little bit of a visual component, which is helpful to a lot of us. The first one, part A here, is saying that we're applying the limit to the contents of these square brackets as x is approaching -2. And what we're wanting to realize here is that we can rewrite this as the limit as x approaches -2 of f of x, and then we can add that, and really I could have put this entire thing in square brackets or parentheses because that's going to be its own individual value, and then we can add that to 5 times the limit, again, or still as x approaches -2 of g of x. And in this problem we're told via this graph that the limit as x approaches -2 of f of x, now f is the magenta colored graph or curve, and as x approaches -2, we can go in here and sort of follow this along on the magenta graph as we're approaching from the left it looks like our y values are approaching positive 1. And as we approach a point that has an x-coordinate of negative 2, from the right, we do swoop up there at the end, and we're pointing at this hole on the graph, which looks like it should have a y-coordinate of positive 1. Remember, we don't care what's happening at that specific point or when x actually equals negative 2. We just want to know what's the tendency of those y values. What are they heading toward? And in this case, that's a positive 1. And then we'll add that to 5 times, and then we'll look at this blue graph, which is more linear in nature. That is our function g. G is also heading toward a point with an x-coordinate of negative 2. So I'm going to grab my highlighter. I'm going to come in from the left toward this point that has an x-coordinate of negative 2. Looks like it has a y value of negative 1. If we come in at it from the right toward that point that has an x-coordinate of negative 2, we are still trending toward a point that has a y-coordinate of negative 1. So we're going to say that the limit as x approaches negative 2 of g of x is equal to negative 1. So we have 1 minus 5. That is equal to negative 4. Perfect. So just taking a quick look, double checking my work. On f of x, we were at positive 1. On g of x, we have a y value of negative 1. We did the multiplication, we added, looks good. In part b, our x value is heading toward positive 1. So realize that in part b, we could rewrite this as the limit as x approaches positive 1 of f of x plus the limit as x approaches 1 of g of x. And then you want to go through that very same process of trying to determine what those limits are, and our hope is that they exist. If they don't exist, then we won't be able to answer this question, or rather, if one of them doesn't exist, we won't be able to answer this question. I also wrote that as a sum, and it was intended to be a product, so we should have a multiplication symbol in there. And the limit of our magenta function f as x approaches 1, it looks like we're going to be in this neighborhood when x is equal to 1, and I'd say whether you come at it from the left or from the right, you're approaching a y value of 2. So let me slide this over, and I will write equals 2 times, and then let's look at the g function. On g, as we come in from the right, it looks like we're approaching a point with an x-coordinate of positive 1 and a y-coordinate of negative 1. On the g function, as we come in from the left, it looks like we're approaching a point with an x-coordinate of positive 1, but a y-coordinate of negative 2. And because of that discontinuity, because the limit from the left is not equaling the limit from the right, we cannot actually conclusively say what the limit of g is as x approaches 1. So unfortunately, this is undefined, and so we're going to say that our answer to part B is undefined, or DNE for does not exist. And then go through a similar process for part C. The g function in part C is definitely the one that we need to be concerned with. As x approaches positive 2, does our function g approach 0? And in fact it does. And so that division by 0 is going to cause us a problem, and we're going to have to say that this one is undefined or does not exist either. In some cases, DNE or undefined is not going to be the answer to part C. It depends on the author and what kind of an assignment it is that you're working on, because the numerator of that statement right here, this function f, as x approaches positive 2, let's look at our graph. It looks to me like as x approaches 2, our function is positive 1.5. I would bet that the limit is equal to 1.4 or 1.5, which is a positive value. And if you take a positive value and divide it by 0, there are some who would say that equals positive infinity. Positive number divided by 0 equals positive infinity. It's a stylistic question. You could get hyper-mathematical on it and argue that it shouldn't say that because infinity is an extended real number and we're operating in the realm of real numbers. We're not going to go bananas with that. Just realize that the answer to part C could be DNE, could be undefined, could be positive infinity. We've got some solutions worked out. There's our -4. There's our solution for part B. We see that these two limits do not exist, so that posed a problem for us. The answer to part B, this author says, does not exist. Here we are seeing in part C a 1.4 and a 0. We can't use law number 5 because of the denominator of 0. And the question is posed, what do you think happens to the graph of f of x divided by g of x? My answer to that is it's going to trend toward positive infinity because we're taking a positive number, 1.4, and dividing it by 0. Positive infinity. I think that graph would swoop upward and have a vertical asymptote. The product law said that we could distribute the limit to f times g, was how we saw it originally presented. Realize that when you're taking a function and you're raising it to a power, instead of f times g, this is f times f. So the limit as x goes to a of f of x times f of x would equal the limit as x goes to a of f of x times the limit as x goes to a of f of x again. Well, this thing is the same as this thing. So if we get an answer of 4 here and an answer of 4 here, we could certainly write that as 4 squared, which is why we're being told that we could evaluate the limit once and get an answer like 4, and then we could raise it to whatever power is equal to the number of times that the multiplication is happening. So just be aware that this is directly related to the product rule. We're just multiplying the function by itself instead of by two different functions like f times g. These are some super specific little features we have. If you're working with a constant function, it doesn't matter what your your x value is trending toward. The limit is going to be equal to c because all of the values are c, because it's a constant function. And in number 8, this is another very specific example. X to the first power is a very basic version of a polynomial, and limits of polynomials can be evaluated by direct substitution. So in this case, we would take this a value, plug it directly into that polynomial, and we would get out an answer of a. And we're going to see some other instances of evaluating limits of polynomials, and you'll hear me remind you to use direct substitution. And if we combine those two properties together, see what we have here is our variable being raised to a power, and if we take the a value and by direct substitution we plug it in for x, we get a to the n, right? So you start taking all these properties and you put them together, and all of a sudden, let's say bx squared plus cx plus d, if you took the limit of that entire statement where x is approaching a, You can distribute the limit over addition, so it would come in here, and the limit would come out to here, and the limit would come out to here. And then you could factor out this b value from the first limit and factor out the c value from the second limit, and then you could apply the power rule in here, which is really the product rule where the function's being multiplied by itself. But you're going to have all of these x values being raised to integer powers, and you're going to have a constant value, so you're able to solve the entire thing using direct substitution. So what we'll do is we're going to skip tearing apart this entire thing, and we're just going to plug the a value in for x if the expression or the function that we're working with is a polynomial. You know that expressions that are written in radical form can be converted to exponential form, and we just saw that we're able to work with exponents. So it shouldn't be a big surprise to you that we can do direct substitution here, and essentially these radicals get interpreted as exponents. So rules number 9 and 10 are directly related. Smash them together, and you've got rule number 11. So it applies to not just square roots, but nth roots. And here it is stated formally, the direct substitution property. You're allowed to just take that a value and plug it in place of x as long as your function is a polynomial. And your a value has to be in the domain of that polynomial. Or if you're working with a rational function, it reminds us, that's okay too, as long as your a value is in the domain and doesn't cause division by 0. You can take that a value and just plug it in. So this theorem is pretty important. This is one that we definitely need to keep in mind. It's not one of the limit laws, but this is a big one. Is every square a rectangle? Well, rectangles have sides that are parallel and they've got 90-degree angles, and does a square have sides that are parallel and 90-degree angles? And yeah, sounds like every square is a rectangle. Is every rectangle a square? Definitely not. Right, squares have to have all equal side lengths. A rectangle just has to have opposite sides with the same side lengths and all 90-degree angles. So a square is a rectangle, but a rectangle is not necessarily a square. It doesn't go both ways. This statement and this statement, which is sort of a compound statement, those statements go both ways. If the one on the left is true, then the one on the right is true. And if the one on the right is true, the one on the left will be true. For sure. Every time, every time, every time. That's what if and only if means. It means that the truth is bidirectional. If A, then B, and B, then A. All right? And what this says is that if we're being told that the limit as x approaches A exists and it's equal to L, then for sure, as you approach from the left and as you approach from the right, you'll be approaching that exact same y value or limit value. If there's ever a question of does the limit actually exist, the way that you're going to determine it is by examining the limits from the left and from the right and determining if they equal each other. If they equal each other, then you're in good shape and you can say that the limit exists. This is an inequality statement regarding limits. That's good to know that you're allowed to do that. And number 2 builds, or if you take a couple of number 2s and put them together, you get a number 3 here, which is called the squeeze theorem, and we're going to see the squeeze theorem in motion in a homework problem, or even a couple of homework problems. But what it says is that if this function g is between f and h, and when I say between, remember that this is a y value. the x value is tucked inside of here, but when you take the x value and plug it in, f of x actually represents a y value. So what this is telling us is that the y values for this function are always between the y values for these two functions. And if I've got a y value for my g function that's between f and h, and I take f and h and I compress them or squeeze them together, it leaves very little room for any kind of variations in the y value of my g function. And if I can take the h function and the f function, and it so happens that their y values become the same value, well, g still has to be in there, so the y value for the g function must necessarily be the same as f and h. If you take a sandwich and you smash those two pieces of bread together hard enough, there's not going to be anything left between them. It's just going to be bread all the way through. And that's what's happening here. That's why I don't like bagel sandwiches. I feel like when I bite into a bagel sandwich, the bagel just compresses and I lose everything in the middle. It's so annoying. Here's a visual illustration that thankfully does not involve a bagel sandwich, but what's happening here is h is the upper function, that's the green one, and f, the lower function, the blue one. Those are coming together at a, and you can see that where h and f actually meet or touch, they squeeze that g function between them, so that necessarily at this point the three of them must have the same y value. So if your limit for h is coming in here and it's approaching a particular y value from the top, and as you come in from the left on your f function, the y values are approaching a particular value from the bottom, they end up squeezing that g function between them, and you end up with a g function that will necessarily have that same limit, whether you're coming in from the left or coming in from the right. And these notes are set up to have a you try it problem. And we're going to be trying some problems by going in and looking at the homework. So let's do that. Let's go check out and see what a homework assignment would look like. And here in number 1, this is a slightly different setup for this kind of a question. We saw it visually before, but here we're being told the value of a bunch of limits. They are all the limit as x is approaching 2. So they have that in common, that's important. And the limit as x approaches 2 for f of x approaches a y value of 9. For g of x, we're approaching a y value of -5, and for h of x, a y value of 0. And so in this first problem, again, we can sort of do some distribution. We've got the limit as x approaches 2 of f of x plus, let's factor the 3 out, and we'll multiply it times the limit of g of x as x approaches 2. And the problem tells us, toward the top of the screen there, that the limit for f of x is equal to 9 as x approaches 2 plus 3 times, and then for g of x it's equal to -5. So you've got 9 minus 15, which equals -6. Not bad. That was bad. That's better. Figure out the limit of g of x. Cube it. Figure out the limit of f of x as x approaches 2. Square root it. In part D, you have to do a little bit of multiplication up here, evaluate what this is, and do some division. And in this problem, the limit of your denominator sends you off to 0, so you've got division by 0. Make sure you read what the problem says. It's looking like it does not exist if you end up with division by 0, as opposed to positive or negative infinity. And I'll let you finish the last one there. This is a graphical approach to that same kind of a question. We already talked about that. And I'll remind you that if the limit from the left does not equal the limit from the right, then the limit does not exist. So it's possible that you're going to have to answer some parts of these questions with a DNE for does not exist. So just be careful there as you're evaluating these. So here we're not given a graph, we're not given any predefined limit values, but what I'm noticing is that this could be written as the limit as x approaches 2 of a fraction where the numerator is a function and the denominator is a function. And so we can use those same kinds of rules like the quotient law, things like that for limits. The problem here is that even though the numerator and denominators are polynomials and we should be able to evaluate their limits independently by direct substitution, in other words, take the a value of positive 2 and just plug it in for x, if we plug a 2 into the denominator, we're going to get division by 0. So have we run into another example where we have does not exist or something like that as our answer? In this case, we're given enough information that we don't have to answer with DNE. I know that because I've already done this problem. I did this problem the first time I made this video, and then I discovered that none of the audio recorded. So I'm doing all of these for the second time. Notice that the numerator, but I'm over it. It's okay. I understand that sometimes we have to go back. A couple steps backwards to keep taking the steps forwards. If we take a close look at this, we realize that the numerator can be factored, and we end up with a factor of x minus 2 in the numerator and 1 in the denominator. When you can cancel out two factors like this, that's called a removable discontinuity. Graphically, a removable discontinuity shows up as a whole. If we hadn't had this x minus 2 up here, we would have been stuck with the x minus 2 in the denominator, which would manifest as a vertical asymptote. When you've got a vertical asymptote, that's when you start getting answers of either DNE or positive or negative infinity, sometimes depending again on the author or the multiple choice options offered to you. But in this case, we get to just cancel it out. We're left with x minus 5, and I've been bad. I should have been writing the limit in here over and over again. So squeeze in a limit as x minus equals or approaches 2 there, and this, the limit as x approaches 2 here. And since this, x minus 5, is a polynomial, we can evaluate it by direct substitution, plugging in the positive 2 for our x value and getting a final answer of negative 3. So again, if you can simplify the rational expression, do so, especially if it helps you avoid division by 0. This looks like it has the potential to also cause the same kind of trouble. The 8 squared in the numerator is 64 minus 64 is giving me a 0 in the numerator. A 0 in the numerator isn't necessarily a problem. However, if the denominator is also a 0, then you've got a problem. 0 divided by 0 is called an indeterminate form and is something that we need to avoid if possible. So I will ask you to factor the denominator and factor the numerator. Your numerator here is a difference of squares, and if you don't recall how to factor a difference of squares, you should be able to look that process up, whether you look to videos or just a text solution process for factoring a difference of squares. Double check that. The denominator is made a little bit more difficult when it comes to factoring because you have a leading coefficient other than 1. I recommend factoring by the AC method. You should be able to locate videos or even some text by searching for that title or that factoring process. Then You may not need to even do any of this factoring, because if you can take a -8 and plug it into here and you don't get 0, then you got nothing to worry about. If you end up with 0 divided by 5, then the answer is 0. If you end up with 0 divided by 0, then you need to start factoring and trying to reduce. And then do direct substitution. And then hopefully you won't have division by 0 anymore, and you'll be able to give an answer. If you factor and you reduce and you still end up with division by 0, then your answer is probably going to be DNE. The numerator here cannot be factored. The numerator by direct substitution is equal to 0, and this one I can do in my head and tell you that the denominator is also equal to 0. So this is definitely a 0 over 0. The denominator is a sum of cubes, and you should know how to factor a sum of cubes, and even if you don't remember, you should be able to look that process up and find the pattern, do some factoring. I can tell you that there is an x plus 4 on the top, and you will find that factor of x plus 4 on the bottom when you factor. So do your due diligence there and remember or remind yourself of how to factor a sum of cubes. And then you'll end up with a 1 in the numerator and hopefully a not 0 in the denominator. This problem clearly gives you 0 over 0, so it's very reminiscent of the previous couple of problems that we just talked about. Will we be able to avoid a DNE in this particular problem? Maybe. Consider that this denominator could be written as 9 plus x over 1. So if I wanted to write it as a fraction, I could write it as over 1. This numerator, you can add two fractions together, but of course you'll have to find a common denominator. So take the time to turn this into one fraction. This is already one fraction. Then you'll have a fraction divided by a fraction, and you can implement keep, change, flip. Once you've done keep, change, flip, if it's possible to reduce or cross cancel, you may be able to avoid division by 0 here. You absolutely will. And after you reduce, you're going to get a numerical value. And don't let the numerical value that you get throw you off. That answer is okay once you've done keep, change, flip, reduced or canceled or cross-canceled, however you like to say it, and then you should be able to solve by direct substitution. This particular fraction is the result of applying the difference quotient to a particular function x to the third. If you don't remember the difference quotient, look that up real quick and refresh your memory as to what the general or generic version of the difference quotient is. And then we take it and we combine it like nested functions like f of g of x or fog notation. This time the fog f of g of x told us to take the g function in this case was x to the third, and we plugged it into the difference quotient, and the result was this entire lousy looking thing. And then we took the limit as h approaches 0 and applied it to it. And what you need to do is multiply this out. If you remember the binomial expansion theorem, you should be able to multiply that out very quickly. If you don't, then you've got some foiling and then some more foiling to do. The good news is after you do all that multiplication, you're going to be able to combine like terms with that x, with that minus x to the third, so that they'll cancel out, and then you'll have a bunch of terms being added together. I don't remember how many. I think it is, maybe it's 3. 3, 4, 1, 3. I think it's 3. you'll still have this h in the denominator, and you'll need to reduce with all three terms. Don't forget to distribute your division. I know that I'm giving this to you in generality, but it's important that you're thinking through some aspects of this on your own. And here in number 8, we have a function over here, and a function out here, and a function in the middle. This screams squeeze theorem to me. In order to evaluate this limit as x goes to 3 for f of x, which is the function in the middle, my hope is that the limit as x approaches 3 for this function and for this function approach the same value. And if they do, and for sure f is in the middle, it's the bagel sandwich. Let's see if it turns into all bread all the way through. Number 9, same thing. Number 10 involves an absolute value statement, and you can look up a more detailed process for this. The absolute value function is actually a piecewise function. Just the regular absolute value of x is defined as, that was terrible, is defined as equaling x if your x values are greater than or equal to 0, and it's equal to the opposite of x if you're working with an x value that's less than 0. For example, if I give you an x value of -2, -2 is less than 0, so I take the -2, I plug it in here, I negate it again, and it turns into a +2. And you know that the absolute value function returns non-negative numbers. Okay, we don't get any negatives. It could return a 0, but non-negative. So the fact that the absolute value function is a piecewise function can make the evaluation of this limit process a little bit more difficult. However, we're approaching an x value of 6, so just make sure that you think through this process approaching from the left, where your x values are less than 0, and imagine or process it where you're coming in from the right, where your x values are greater than 0, and make sure that those two limits are equal to each other. All right? Effectively, you're going to be able to do this with direct substitution, because once you take an absolute value and you break it up into these two separate statements, you'll notice that both of those are polynomials. That's a variable to a power. So you will be able to use some direct substitution in this. Just make sure that as you come from the left and come from the right toward that x value of 6, that the limits are equal to each other. Number 11, same idea. It's a piecewise function. You are being asked initially to choose the graph of that piecewise function. I think that's great that you're going to do that first, and then there are some limit questions coming in after that, where some of them are one-sided limits, some of them are trying to make sure that the limit from the left and from the right equal each other. And then here we've applied the absolute value to the function. Now, the original function that you were asked to graph did not have an absolute value wrapped around it. So in part D below, we're putting an absolute value around this function. That's going to change your graph. Think about how an absolute value would change your graph, and then maybe sketch that graph, and then think about an answer to part 4. I called it part D before. Yet another piecewise function. Here, the order has been reversed. You're being asked to evaluate these different limits, and then you're being asked to determine which of these is the graph of your piecewise function. You can choose to select the correct graph first, or to try to evaluate these expressions and these limits. Realize also, just notice, that's not a limit question. They just want to know what's g of 1. Probably because we just finished approaching 1 from the left and approaching 1 from the right, and now we're going to compare it to what's actually happening at g of 1. And the same thing is happening for the next three parts. From the left, from the right, and the limit. Now this one is a limit statement. All right. In order for a limit to exist, the limit from the left must equal the limit from the right. And that's it. So that's what a homework assignment is going to look like as pertains to one-sided limits and using the limit laws and that relationship between your two one-sided limits from the left and from the right, and that if those two are equal to each other, then we can say that the limit exists. And if we're being told that the limit exists, we know for sure that the limit from the left will equal the limit from the right. All right, I will see you in 2.4. Before you join me for 2.4, go make yourself a bagel sandwich, because 2.4 is conceptually a little brutal. It's got some process in it also, but I'm going to bend your mind a little bit. See you there.